Okay, so feature engineering and model tuning. So has, discussed before, is this the stage that we really have to do this in? Well, no, because you're going to do some feature engineering obviously before. Um, but this is the stage in which, we haven't met the business goal. It's kind of a given that you're doing feature engineering up front, as far as like when it comes to, pre-processing, visualizing your data, massaging your data, adjusting for either lack of, richness in the data set, so no dimensionality, lack of features, or just the sparseness of the total data set in terms of numbers, right? Um, but let's say you're trying to basically figure out how to, your model hasn't met, you've evaluated your model, it's not meeting your business goals. How do you then correct it, right? So this one's about feature engineering. I don't know that we talk a lot about data augmentation, but it's there, right? It has an option. So this is focused really on feature engineering, some hyperparameter tuning, right, to improve the results of your model, and just really the general concept. We're not necessarily going to go through every single hyperparameter that you can tune for your particular model in question. It's not going to happen, right? And then, oh yeah, so I guess I'll create a hyperparameter optimization job. Then we'll summarize, and then tomorrow we're actually going to go through lab 4. Now, I don't expect to get through all of this, although we might. So here, by the way, here we've got, dates, we got visitors, we got sales, right? So you're really not necessarily adding new like dimensionality or data per se. Well, actually, let me rephrase that. You're not adding new data per se. In a sense, you might just be adding more dimensionality to the data, like another feature to the data set, in order to make it more relevant for the problem that you've tried to solve, right? So, for example, in this particular example, you might say, well, why are sales so much higher on these particular days? Is there something that we're not either categorically or numerically, and ultimately it all ends up being numerically, that we're not accounting for, because it's like 30% of customers made a purchase on these 2 days? Is there some other context or some other value or some other dimension that we can add to the data set that is just an extraction, not even an extrapolation, not even an assumption, not even necessarily an inference? Is there some other piece that we can add to this to make it richer and more relevant for the problem that we're trying to solve? So, for example, here they're adding days of the week because, well, sales are higher, right? So this might be influencing purchasing habits, especially if you're like a retail store versus online, although, you never know. So, because customers are more likely to buy on the weekend because they're more relaxed, they're not focused on work, they don't have school going on, they don't have all these other distractions, right? And again, those were all assumptions as to the reasons why. Were they good ones? Maybe. So if we can engineer a feature here, which is just an extra dimension of the data set that calls out the day of the week, and then we can just input that data automatically, right? So just know that this is the kind of thing that we're talking about with feature engineering. Is, are there ways for us to, extract more meaningful information for the problem we're trying to solve with the data set that we have? So we could, extract and increase dimensionality. We could reduce dimensionality, right? We could extract features that we consider more meaningful. We could condense, right, highly correlated features and find some commonalities between them. So the first two, feature extraction and selection, typically are going to reduce the dimensionality of your data set. Obviously, like in this case, we created a feature, right, or transformed an existing like date in this case to another variety. By the way, you could also do this, as a variety of data augmentation. Like if you're trying to classify pictures and you need to add more variety to your data set, turn pictures, flip them, turn them in different ways. Just like just now with the confusion matrix, where we were kind of testing our ability to understand what all the values mean if they're flipped in a different context. Same thing here, right? We are going to train our model better if we give it more variety to the data it sees, right? So, there is a thing though where dimensionality, right, refers, to the number of features or kind of inputs that you have in your data set. So it's all the characteristics of the data. So the curse of dimensionality refers to the fact that models will have a difficult time finding the patterns you want them to identify if there's just tons of dimensionality to the data. It's like many features to the data, many columns to sort through. That's why obviously having the relevant columns is important. Reducing things like correlation, making sure it's meaningful and relevant, right, to your data in question. When I say reduce the correlation, reduce the number of correlated features inside of your data set. But again, it all just depends on the problem you're trying to solve. So, for example, if you wanted to extract features, right, to reduce the dimensionality of your data, like image recognition as an example. Before neural networks, one of the ways to handle image data sets was just to extract features from individual images. So if it's a car, in this particular case, you might extract like it's got a windshield, a headlight, and tires, independent features. So instead of having raw pixels kind of making up your data set, you could basically have features or columns such as, is a windshield present, is a tire present, is a headlight present, I don't know if license plate would be appropriate, but these features, if present, would make it easier to learn from the image data and eventually start to recognize, for example, is it a car? Or faces, right? Are there eyebrows? Are there eyes? Are they a certain distance away from the nose? Is it of this regular size? What are the lips? Are they generally within this bounded dimension? Like there's like things, are there ears, right? There's things to consider that are common to most faces. So other ways to approach this, obviously, right, is any form of clustering, aggregation, or condensation. NLP, for example, to extract out like popular words, PCA or principal component analysis, or TSNE, right, which is basically to reduce the dimensionality of highly correlated or clustered or similar kind of like dimensions or data sets. Get it. You got to be careful because sometimes you can reduce something that is incredibly relevant for the business problem you're trying to solve and the algorithm you're trying to use. So it's not like you couldn't get it back, but it can reduce high dimensions in data if you're concerned about that. One of many. And then feature selection, particularly when you have, again, correlated values or things that are maybe more absolutes or means or just indicators of like differentials like change, that may not be exactly what you're trying to predict sales. I need revenue, right? So, because revenue should shift in parallel to sales, right? So it's not going to provide more insight to the model than it's already getting from the sales data. So then why would you need the revenue data, right? The other thing is that the net sales may not the net change, for example, in revenue, that may not be, or that could be net profit. I'm actually not sure. What does it say? Yeah, oh, this is net profits. So net profits may not be relevant here in this case. So you can just remove that feature because it's not relevant, right? And then these become the selected features. Are they relevant for the business problem? Absolutely. You really want features in your data that are the most useful to the problem, right? Because remember, particularly if you have features in there that are not relevant for the problem, then you're going to get a lot of noise. And you're going to have problems being able to like converge and find them lost and kind of like analyze the patterns and understand the relationships in the data. You're going to have trouble with that if there's too much noise in the data. Now, obviously, when you have too many features in your data, you should filter down to kind of what you need to do that. Filtering the data is just a common, right, technique that you'll use for feature selection. Machine learning algos are not used just for typical structured data sets. Remember, sometimes you're dealing with other formats like video and audio, images, text, that kind of thing. So for those types of data formats, the data structure is more complicated and filtering needs to be like more specific to the problem. For example, if you're identifying cars, you still need a sample set of everything that's not a car, particularly similar objects like trucks, vans, if you have to get that specific. But having pictures of like ducks may not be relevant, right? But it depends on how much not cars you want, right? You could also, by the way, say, well, what if you're only like interested in the departments that are underperforming? Let's say it's the seasonal department. And so, swimsuits in this case. And if it's wintertime, maybe it's winter coats, or ski equipment or guns or what else have we run into? Right. So this is like a clothing data set, includes 10 years of sales data. But what if your business problem is only actually focused on swimsuit sales? Do you actually need the entire set of data? Maybe not. And maybe you're only really interested in spring and summer because the amount of sales during the winter and fall as it relates to swimsuits is so incredibly low. It's not even remotely relevant. So in this case, for example, right, you could filter out the quarters that don't make any sense. Other things, right, like with feature creation and extraction, either like day of the week, which was the first one we saw, where we basically created a new dimension by putting day of the week in there, which gave more meaning to the higher sales numbers because it showed basically that weekends tend to correlate with a higher sales number. But like with this, this could be everything from extracted to dates of last purchase, looking for holidays, right? Maybe also extracting a little bit more into seasonality, because maybe it's like, how do you classify summer, winter, and fall in a more temperate climate, right? Like in Atlanta, just as an example, February, March, and April, that's tends to be when the spring shows up. And then past April, when we start getting into May, May, June, and July, and August, our summer is a little bit longer and it tends to be a little bit hotter. So like we can end up with 90-degree weather from May, June, July, August, sometimes in September, right? So our summer is a longer season. So things like having dates like this could also inform even those larger buckets as far as like giving richness to that. Because like if we're selling swimsuits, maybe we care when it's warm. So maybe it's not even about date. Maybe we just need some weather data, right? As an example. So, and unless, by the way, your algorithm has a great way of dealing with dates, you probably want to extract it out into kind of more separate columns in this case. So you could generate your own like a month, day, and a year feature instead. Again, depends on the problem you're trying to solve. Oh, I realized that I'm missing chat. Hold on. Sorry, hold on. Actually, let me back up for 1 second. So let's see. So Rachel, just to back up, sorry, and I apologize for not seeing this earlier. Were you asking, is that entire file system on the S3 bucket I named in my notebook? Actually, no, it should actually be on the file system that the notebook is running on. Now it will output the S3 like model. If you like put that in there, it'll output it to the S3 bucket that you specify. So just know it'll be there as well. Let's see, and other questions here. We're talking about filtering rows, not columns. So just to go back and make sure. Sorry, I missed that. Yes, for example, we might take out all of the rows related to that, like the fall and winter season, just assuming that that's what you're asking. In other words, we might reduce our data set from a row perspective where the date equals like this date range. So in Atlanta, let's assume that spring and summer are really our only times where the weather gets warm. We might be looking at all the sales data from, let's say, because February is still a little cold, but let's say all the way from March all the way down to September, because that's when peak season is going to be, right? For as far as like swimming pools in Atlanta, October, November, December, January, February, we'll let those out. Well, we'll take those out, right? So that all those rows will be dropped, not just the columns. Now, the techniques you use for creation and transformation obviously will be different depending on whether you're dealing with numerical or categorical. Here, for example, like for numerical features, some of the techniques include maybe taking the log of the square root of the cube, right? It also might involve techniques such as binning, where you can have group things together. or even some kind of like scaling standardization, right? So let's look at some of these methods. So taking the log of a feature, like a number, is a common transformation method, right? It's really just to change the shape of distribution, right? Because it might be, it has X and Y and relate to each other. It might be just be a little skewed, right? It's really used to reduce right skewness of features. But just to say this, the log can't really be applied to zeros or negative values. Now, you can't apply square root to negative values, but cube you can apply it to negative values, right? So that works fine. But it could be like, for example, the area of an apartment or the total cubic volume of rainfall over the course of a year. This also has an effect on the distribution of the feature in question, but the impact is not as significant as logarithmic transformation. So taking the log, right? So, yeah, it's basically, again, to reduce skew in the distribution of a feature. Now, binning is where you convert like a wide range of values into, groupings, basically. And so, binning can go, where every bin is at like the same value. So 5, 10, 15, 20 represents every bin. Or it could be something kind of along this lines, especially as it relates to age, where, hey, are you a kid? Are you an adult? Or are you a senior citizen? This, by the way, can convert a continuous variable basically into a categorical variable. Has a smoothing impact on input data and is going to reduce wide ranges of continuous variables. So particularly with a small data set where that wide range of that continuous variable is going to have a lot of influence inside the model, it can like reduce these chances of overfitting with these small data sets.
Sorry, can you repeat that? Was there an emphasis on small data sets versus large data sets?
Well, it will reduce the chances of overfitting in cases with small data sets.
Okay.
Because that like broad distribution of that continuous variable is going to have a lot of influence because there's not a whole lot of dimensionality to the data, right? With a small data set. Let me rephrase that. There's not a lot of samples to look at with a small data set, so not dimensionality. So what would happen is that when you have a wide range of distributions inside of that small data set, it's going to carry a lot of weight, right? Because you don't have a lot of samples. So you got to be careful with that. Yeah.
Thank you.
You also might need to scale the data. Probably like binning can help with that. Scaling is probably the other thing you're gonna look at, right? So for example, here, if you look at the bedrooms, like it just ranges from 1, 2, 3. Let's say it even went up to 5, like just to throw that out. And of course, the square footage should go up with the number of bedrooms, right? Ideally, although, there might be other things that vastly increase the square footage as well. But notice here, it's like, if they're trying to, for example, because I see a label of loan approved, if they're trying to predict loan approvals, what might need to happen here is that, bedrooms is only going to scale, let's say 1 to 5, or in our example here, just 1 to 3. But the price range is going to range from as low as 325,000 to 1.3 and change million, right? So the problem is that the range of these features is dramatically different. Like one is 1 to 3 and the other is 325,000 up, right? So that's a huge difference in scale. And so because it's so disproportionate, the model could give influence to the larger scaled variable, variation of what I was talking about before. So price is going to maybe perhaps have a like heavier weight to it, right? And not all, by the way, machine learning algorithms are sensitive to different ranges of data, but a lot of them are, right? So a wide range of data is going to like be very difficult to get to optimization, right? There are exceptions. Like for example, decision trees, like in random cut forests, are usually not sensitive to the scale of variable in the data sets. There's lots of others. So then how do we scale things down? How do we basically, in a sense, kind of standardize them to a certain degree? So we're going to apply, you would apply a transformation to a particular column, and different columns are scaled independently. So you're only going to use the data in a specific column to do the scaling. So it's just that one column that you're going to scale against. Now, these formulas, by the way, are not covered. But one thing you need to know, I don't know why this was on the exam. This one really threw me, actually, is that they were like, it was like the question was, in scikit, what is the mean variance standardization called? Like, what is the name of the scalar? And it was like standard scalar. I just happen to remember that from, right, tons of having to deal with this, right? But I was like, oh, standard scalar. I was shocked. I was like, yeah, that's the only answer, because the other options were min max scalar and max ab scalar, and I was like, so weird. Anyway, this is probably considered at least the most widely used scalar, right? Using the mean and the variance. It definitely keeps the outlier information. Like, let's say you have values from 325,000 to 1.7 million. Like, it's going to keep the outlier information, but it's going to reduce the impact of the outlier, right? In particular. So after scaling, by the way, the feature is going to have a mean of 0 and a standard deviation of 1. And so you just use standard scalar for that. Now in min-max scaling, right, this is another widely used method, right? You just find the minimum value and the maximum value for the feature you want to scale, and then you subtract the minimum value of the feature and divide it by the difference from the maximum of the feature and the minimum of the feature. So the new variable is, again, going to be between 0 and 1, right? And this is just calls the min-max scalar from the scikit package. So remember, just in terms of like options, there's the mean variance scalar, which is called by the standard scalar. There's the min-max package. Once again, still minimizing outliers, and still we're providing values between 0 and 1. So it takes a wide range of a continuous variable and just shrinks it between that 0 and 1 value. You can see some outputs from the arrays there where it's like 5, 3, 2, 2. And then it's just going to scale it down to 1, 1, 0.1666667, and then 0 dot, just 0 at that point. And so it's just going to scale that within those range between the maxes and the mins. The advantage, by the way, of min-max scaling is typically that it's going to be, it's great. It's very like appropriate for cases with a small standard deviation. Because remember, the difference between the maximum and the minimum is usually going to be larger than standard deviation. So it doesn't really change the distribution of the feature. And due to like the decreased standard deviation, what's going to happen is outliers are going to have a little bit more of an influence here. So it is recommended before you do this transformation from min-max that you actually handle the outliers, because it's not going to have the same minimizing effect against outliers as the standard scalar function is. And there's max abs, another scaling method. So we talked about mean variance or standard, and then we've got min max, and then we've got max ab scaling, right? So max abs doesn't destroy like sparsity because you don't center it through intermittent measurement, you just scale it, right? So it divides all the data in a feature by the maximum absolute values found in that feature. So they're just going to really test your knowledge about, do you know like what the options are? They're not going to necessarily have you like apply them. The only thing that the question again that I did get was about the standard scalar. They did ask me about minimizing outliers, and they kind of compared these three, and standard scalar was the option. And I don't remember the details as to why that was, but min max, max abs, and then there's robust scaling. So this one's going to focus on like the different quartiles, right? With like the percentage of answers that, for example, if it's 25, like there's 75% that were above the line and 25% below this line, right? Depending on where that number is. So with the quartiles, right? When you find those three quantities, in this case, the median, the 75th quartile, the 25th quartile, right? Which median basically is the 50th quartile. what you're going to do is you're going to figure out those three qualities. And then in this case, you're going to subtract the median of the feature and then divide it by the difference between the 75th and 25th quantile of the feature in the training data, right? So it's going to be robust outliers because outliers are going to have minimal impact when calculating medians or quartiles. So robust scaling was not one of the options when it talked about basically minimizing the impact of outliers. So, but that would have been probably one of the best options. Notice it calls the robust scalar. I don't know why. This is one of the few syntactical things that it seems that Amazon checks on, but max-ab scalar, min-max scalar, and the standard scalar. Wait, where is that? Here it is. Standard scalar seem to be things that they check for from a syntactic perspective. I don't know why. Other things to think about is that, you know, in addition to numerical transformations, there might be transformation techniques that you want to follow for categorical data. So for example, right, if it's ordinal, where it's ordered, you know, converting that into a number isn't necessarily inappropriate because there's meaning in the order of the categories, right? And whether that's sizes or, you know, level of education, just remember that when you convert a category into a number, by default, when numbers increase, right, typically depending on the algorithm, that's going to mean something to the actual model. But if the categories are not ordered and you decide to just randomly assign numbers to that, well, that's not, that it's going to assign meaning where there's actually none there, right? So for example, if you look back at the housing data set that we were looking at, we've got several features here, like 1, 2, 3 bedroom, we've got square footage, we've got garden size, right? Obviously in home price. There's also the label at the end, right? Whether the home loan was approved or not. Now, what happens here is that, and again, depending on what the small, large, medium, and not applicable actually mean in terms of like sizes, like the ranges, for example, is a medium actually double the size of a small, or is it just an incremental increase? Is a large double the size of a medium, or is it just an incremental increase? For example, here, what they're saying basically is that a small is a 5, a medium is a 10, and a large is 20. So they literally are saying that a medium is double the size, garden size wise, than a small is. And they're saying that a large is double the size. And that might be a perfectly natural and normal conversion because that is a, right, ordinal classification. It has, the labels have some kind of like size meaning in relation to each other. They have some increasing or decreasing meaning depending on whether you go up or down the categories. So this kind of transformation appropriate. Now, here though, by the way, if you assign a number to things like house, apartment, condo, you know, you might be showing some bias, right, in how the model like is going to interpret that. And you probably don't want that because these are just differences, right? I mean, although some people would say, well, you know, owning a condo is better than owning an apartment, and a house is better than a condo, and a mansion is better than a house. And where's a mobile home fit in there, by the way? Just kidding. My family is all from the South. They love mobile homes. Anyway, moving on. So if you apply this like 1, 2, and 3, that's going to imply that something has like a numerical meaning, it has a value, right? So they may give you wrong or unexpected results. So this is where, for example, like one hot encoding, or like what we were looking at before, dummy encoding, some kind of encoding is appropriate. Now, they're only going to ask you about one hot encoding. They're not going to ask you about Einheiser or dummy or anything else. They're only going to ask you about one hot encoding and the purpose of one hot encoding. So in this case, what you're doing is you're taking categorical data and you are converting it into numerical representations, right? So in this case, you would take, you know, house, apartment, condo. If mansion was there, mansion would be there as well. and you're basically indicating whether or not it's there or not. That get dummies function, when I was looking at it last night for the dummies encoding, you know, based on our like conversation, if you drop that first value, from my understanding, what it looks like it does is it would basically drop this, because if this was 0 and this was 0, then that would mean it was this, right? Right? So, yeah. So, in other words, if you, and then extrapolating this out, right? If you went to all 50 states and you dropped Alabama, I'm in Georgia, so I feel like I got jokes about Alabama, but we're not going to do that. So if none of the other states match, then like it's safe to infer basically that it's Alabama, right? So, now, is it really? What if they're in like Guam or something? Anyway, regardless, because one thing about this, by the way, is that like this kind of thing might introduce too much dimensionality of the data. And what if your company is not divided by state? For example, it's divided by sales regions, which is actually like, I worked for Red Hat working on OpenShift and Kubernetes and their Knative stuff for a while. And they're divided by region, right? So maybe if they're doing sales forecasts, they don't really care by state. So in that particular instance, you might group it by region: Southeast, Northeast, Midwest, Northwest, Southwest, that kind of thing. That way you can reduce the number of columns and yet still derive meaningful location context in a numerical way. And so like you could still actually take the state data and still make it meaningful. You could even group it differently. You could say, you know, by FEMA region, you could do by habitat, by like environment. Is it coastal? Is it inland? Right? Is it an island? So, and again, it just depends on what kind of problem you're going to solve. But you probably wouldn't necessarily encode, you know, non-ordinal like categorical data into 100 different levels, right? What you might do is actually take the most 10 popular groupings. There's other ways to approach this. But be very careful about adding all of a sudden like 50 different dimensions to your data, unless it's super relevant for the problem. I'm getting a lot of spam calls today. So funny. Huh. All right. Any questions before we move on to hyperparameter tuning? Okay.
I do have a question actually. In that state example, if we were to actually group into northeast, northwest, just a thought here. If we then wanted to explain our model results, and then we'd have to make it clear that we lost some resolution there, right?
Yeah. That's actually a valid point. Every single thing you do or assume about the data, it's really great to capture, but particularly transformations. And the main reason for that is that when someone comes back to you and says, hey, can we get a finer grained report on this? Now, could you go back and reassociate the data with the resolution that you lost? Potentially, right? But it's great to like note that, so that you, like when you forget all the things that you've done from a processing standpoint, whatever, you can go back and methodically look at what you've changed. That's the single greatest detractor I see when people are working through this whole process, is that they're not actually capturing what they've changed or what they didn't change because they assumed it was important. I know that sounds like a lot of work, but it really saves a lot of headache when in terms of like thought processes and how your workflows work, where then that way you can just quickly look back through your notes and say, oh yeah, someone just asked us to make this a little granular, and you're like, oh, you know what, we actually grouped the data down, right? in a sense, kind of bend it, right? We grouped it down, so we didn't actually, we can't actually do that unless we do some kind of like association. In other words, there's extra work involved. So it's a good point.
Gotcha, thank you.
It's funny because a lot of ML work follows similar kind of like patterns of derivation and thinking, like the way that software engineers do it, but the disciplines for capturing the way like that we execute these things from an ML perspective, we don't often all of the follow the same path. And notebooks are super cool, but they also don't foster the same kind of process that software engineers use, which is unfortunate because you know, almost everything is, it's asked that almost everything is tracked nowadays, not necessarily for accountability purpose, but because we're also information overloaded, that without that tracking, it's hard to remember exactly what you were thinking at the time that you did it, right? So
Oh yeah, kind of on that point, I've read about the idea of versioning your data, but I can't remember if I've seen anything about AWS automatically doing that for you.
well, like for example, traditional RDBMSs like Oracle and all that won't version your data, but with S3 and with DynamoDB, you can turn on versioning. So every time you make a
Okay.
change to the data, it makes a complete copy of the data. With DynamoDB, what it does is it makes a point in time delta every time you make a change to the data. So you can literally roll back your DynamoDB database back to whatever point in time you want to.
Okay.
Yeah. But you had, with S3, you would turn on versioning. Now, here's the only problem with S3 and versioning, if you turn on versioning for it to track all changes, is that the changes aren't labeled.
Mm.
So you're kind of making a little bit of a guess about, right, where what change went with which thing. That's where, by the way, operating this in version control, at least, and putting your notebooks in version control would allow you to know about what time frame you made a change, because you could go look in version control and then you could go grab the version of the bucket that, you know, at that particular time. So, because it does,
Gotcha.
they do have timestamps on them.
Thank you.
Yeah. There are companies out there, by the way, that make that a lot easier, that are outside of AWS with their AWS partners.
Yeah, Alteryx was, or that section in that paper, Alteryx was really patting themselves on the back for that.
Good.
I believe them, but
Yeah, yeah, no, they
I've
do.
used Alteryx otherwise, but
Yeah, they do. They do attempt to solve that problem. And they do a good job. Okay. Oh, we're good. We're good on time, actually. Oh, this might be, I know this is going to sound weird, but this might be the first time that I'm actually matched up with the days. That's really strange, actually. Okay, so this is more about the concept of hyperparameter tuning and not what to tune, because I feel like tuning is as much an art as is a science, even though it's all about numbers. So, you know, the idea here is that with model tuning, you know, we've already done what we can to our data. Is there a way to tune the parameters of our model, the hyperparameters, not the parameters, the parameters of our model, to provide even stronger accuracy? So you may remember us kind of like seeing this earlier. We saw this little symbol and it says, hey, we're going to talk about it later. Well, this is later. Okay, so there's a couple of different hyperparameter categories. The first are the ones that, like, you know, help define the model itself, like the, you know, size of filtering, pooling, stride, padding, basically things about how the algorithm is going to work on change itself to a certain degree. It's about the model itself. Now, how the model learns or optimizes, right, towards like the minimum or loss function, that's going to be another set of parameters. So like you may have noticed earlier, one of them defaulted to stochastic gradient descent, right? By the way, could anyone just define stochastic for me, just briefly? What does stochastic actually mean? if we were like to look it up. Yeah, it's just a fancy word for random, right? So stochastic gradient descent, choosing gradient descent, choosing mini batch, right? You know, it can, you know, parameter weights, right? That kind of thing. Initializing weights, learning rate, right? And then data, right? Data parameters are attributes of the data itself, right? This is where data augmentation really comes in, like cropping and resizing images, pivoting images, right? I don't know though that I would consider that like a hyperparameter category. That's more like data augmentation. Just my 2 cents. Now, the best way for you to tune your model is to just go off of guts and glands, right? Just feel the force run through you, run out some expecto patronums, and just do it based on gut. It's going to work out great, right? Now that being said, by the way, it is shocking how someone will get, you know, maybe we should tweak this and see how it goes. Now, obviously, if you want to do this in an automated fashion, manual tuning is not the way to go, right? But that being said, don't be dismissive of someone who's like, you know, we should probably like tweak this parameter and see what happens. Be shocked sometimes how that can yield results. But I would place that in the context of an automated like exploration of tuning hyperparameters. This, by the way, is considered to be very labor intensive, right? Not the most efficient. Now, you could also, by the way, search through every single possible combination of hyperparameters giving a different, like giving a given range, right? So for every like possible combination, you train up a model, scores produced on the validation data. And the only thing you're really changing at that point, because you're not changing the data or like really the model, you're just changing the hyperparameters, right? I say that it could include some model changes. It could include some optimization changes. Really not doing some data changes here. Although you could crop and do other things as the data is ingested, like for images, for example. But grid search is considered to be also remarkably inefficient because, but it's thorough, right? It's super thorough, but it also takes a lot of time. Now, random search, similar to grid search, but instead of training and scoring on each possible hyperparameter combination, a bunch of random combinations are selected, and you can set the number of search iterations. It could be based on time, it could be based on resource constraints. And oddly enough, when compared with each other, random search tends to yield better results over time. Like within a given short time, like within a shorter time frame. Obviously, if you had all the time in the world and all the parallel processing and whatever, grid search would be awesome because you would then get the absolute exploration of every single possible combination of hyperparameters, and you would then truly find the optimal. But remember, we're not looking for the absolute best. We're just looking for the best in the given amount of constraints that we have, which is usually time, money, compute power. So random in that case tends to be a little bit better. There's also Bayesian, right? Search. The only thing that's interesting about Bayesian search is that it does not do concurrency very well. Whereas like random search, like you could kick off a bunch of models as long as you're tracking it. You could kick off a bunch of models with a random set of hyperparameters changed and get back a bunch of results as far as like, you know, whatever metric you're using to track. You could kick those all off in parallel because it's not sequentially learning. It's not modifying based on previous results. It's just trying a bunch of things at random. Similar with grid, the only problem with grid is that the scale at which you're going to do that is going to be way larger than the scale you're going to do it on random search. In other words, you're going to need a lot more model instances to find your kind of like optimal kind of model than you would with random search. But Bayesian is a little different because it's going to make guesses about hyperparameter combinations, and it's going to use regressions to basically refine the combinations. So it's going to learn from the previous run, and then it's going to make some guesses about what to do next, and it's going to continue to learn, right? Because it's going to keep running the combinations to get the best results based on the previous results. So it's going to test the first set of hyperparameter values and then use regression to choose the next set of hyperparameter values. And it's going to continue to do that, but it's very sequential. So let's see. I remember, I don't know if that was in the practice or on the training. I'm sorry, in the actual exam. But there's basically a reference to the fact that adding more kind of like parallel, like horizontal scaling to Bayesian isn't going to help you. Matter of fact, reducing Bayesian search down to just a sequential set of jobs is going to be the best thing, because it needs to learn from the previous job to generate the next job, right? So it's just going to continue to try and improve the metrics by using regression based on the parameters that you used last time. Sometimes, by the way, it will tune small, and sometimes it will tune far removed from the values. It is going to actually explore the range of hyperparameter values that you've given it. It will try to find new areas that are well understood, right? So this, in a sense, is interesting because it uses random in combination with regression to kind of like make the next best educated guess, and it's going to respond to the error rate lowering or whatever metric you're focusing on to try and find the best combination of hyperparameters. I want to be frank about this and to be clear. SageMaker does not support grid search. It does random, it'll search Bayesian, but it will not support grid search. You know, unless something has radically changed in the last week. So that is on the exam. They're going to ask you that. So understanding that grid search is going to go through all possibilities, random search is going to try a set of random possibilities. Both are obviously constrained by time and iteration. Same with Bayesian. Just know that Bayesian, again, is going to not benefit from parallel runs. It needs to stay sequential. Now, here's the cool thing. Amazon does offer automated hyperparameter tuning. So it will let you perform automated hyperparameter tuning. It just finds the best version of the model by running your training jobs on your data sets using the algorithm and the range of hyperparameters you specify. And then it's just going to choose the values that result in like the best performance as measured by the specific metric that you use, right? It's going to use Gaussian process regression, and it's going to try and predict what's going to be most effective at improving the metric or outcome in question, the fit, right? It's also going to combine that with Bayesian optimization to balance exploring this space and exploring the specific hyperparameters when appropriate. So this can be used, by the way, with the built-in algorithms, with the pre-built learning frameworks, and with the bring your own algorithm containers. So you can use this with pretty much all the models, all the different types. Space age chair. So here, for example, let's say you don't want to solve a binary classification problem on a fraud data set. You don't want to. So you want to. So you want to maximize the area under the curve by training a linear learner algorithm. You don't know which values of the learning rates are best. So to find the best values, you just specify a range, and it's going to search to find the combinations that, you know, result in the best objective measure based on what you chose, right? So in this case, it would basically return a job with the highest area under the curve, the highest AUC. Now, one statement that I find interesting in here is that tuning doesn't always improve your model. So you might have ended up with a good enough model, and then you started tuning it and realized that it didn't really get any better than where it started at, the defaults, right? Although generally I would say tuning does yield results. It may not be the massive increases that you're looking for. It just depends on the nature of the problem. So best practices. I'm just kidding. Let's say adjust every hyperparameter, right? Do grid search. No, don't. Limit your range of values to what you think would be the most impactful based on the problem you're trying to solve. So, read the documentation. SageMaker, by the way, is going to attempt to figure out whether your like hyperparameter values are log scaled or linear scaled. It does assume that hyperparameters are linear scaled. If they should be log scaled, it's going to take Amazon, like SageMaker, some time, right? To do that, to discover that, like whether it's log or whether it's linear, right? If you know that a hyperparameter should be log scaled and you can convert it yourself, doing so could improve your hyperparameter optimization instead of making SageMaker actually convert it, right? Or discover that it's been converted, right? So, and depending on what you're using, for example, running more hyperparameter tuning jobs concurrently could get more work done, but like if it's Bayesian, for example, that's not going to help, right? So. In distributed training jobs, make sure the objective metric is the you want is the one that they're actually reporting back, right? Otherwise, you're going to spend your time running a bunch of concurrent jobs and you're not going to get back the metrics you're interested in. Yeah. Okay, so let's create a hyperparameter tuning job. Let me move this out of the way. You go over there for a second.
Hey, Michael, while you're doing that, just a question on the automated side. So it's automated in after we tell it what to optimize for, right?
Yes, with your, you mean for your objective metrics plus the range of hyperparameters that you want it to.
Right. So it's not like you click a button, it runs the model and makes your model somehow better based on the tuning. You have to kind of give it bounds to make it better.
Yes. Yeah, because it's not going to do grid search, right? Right, because I remember we were saying that's not an option. It's not going to do grid search.
Yeah.
Otherwise, if that was the case, actually, you could just let it go. But then how long would that take?
Right. Yeah. I mean,
Yeah.
like not necessarily grid search, but even if it had defaulted to like a random or whatever, just in general, you have to give it those bounds before it automates the tuning.
Yes. Or just accept the defaults. Right. But yes, you need to give it bounds. Did I already have a hyperparameter job? Oh. God, man, I was doing a lot last week. I don't know what was going on. Okay. So let's create a hyperparameter job. Actually, just for a second here. Oh, that's right. These are just linked because I was calling these actually out through code. That's right. These are just listing the ones that I was running. Let's create a hyperparameter job. I think I want to say that early stopping was actually on. Was actually on the, maybe it was on the practice exams. This one might have been on the exam, but I think it was actually, where you could basically like, if you're tracking a metric and you're not seeing it improve as you're running through the hyperparameter job, and there's been a certain number of iterations, you can just say, look, just go ahead and stop, right? We don't need to run through the whole data set again if you're not seeing improvements. So even though I told you could run, 500 times, if you've run 50 times and you haven't seen improvement on the metric, then, our methodology, it's not going to work, right? We need to either change the range or come revisit some parameters. And so it'll prevent you from wasting money and time, right? Time arguably being the most important, right? Okay. So let's see. So here we're going to create a job. The first step is to define some job settings or the strategy that we're going to use. Notice the options here. We can either use random search or Bayesian, that's it, right? Notice that we're following some steps here, right? We are defining job settings. Then we're going to create the job definition. We're going to configure some parameters, input and outputs, resources. and then the tuning job resources, and then we're gonna review and create. So we're actually following, it's not just one page, we're actually following a 4-step process. I wanna make sure that's clear. So I'm not gonna turn on early stopping, although options could be just auto or off. I'm not gonna put any tags in here either, so let's just go to next. Okay. Wait, what do we have this set for before? Hold on. Just kind of looking at my notes to make sure I'm not gonna like completely wreck this whole thing. I think Bayesian was the default. Okay. Now we're on the create the definition page. So let's go ahead and add a training definition. So, you know, let's call it linear learner. Just as an example. Role, I usually just use the execution role. Not going to stick it in a VPC, right? As far as algorithm options, I'm going to just use the default. Let's say we're just going to go ahead and do linear learner. Oof, interface. There's where it's going to pull the Docker file in question, right? Let's see, for we're just going to leave file alone. For metrics, let's use validation objective loss. Now I have that already there, so we'll choose that. We want to minimize objective loss, right? Has an option. Let's see. In the hyperparameter configuration. Now, again, you're gonna have to like run through the documentation to really understand what all of this is. So I'm actually gonna post this link in here for those you can see it. And I put some like random kind of values in here. Where did you go? Where's chat? There you are. So let's see, for my notes, the mini batch size is going to be integer linear. So let's do 200 to 500, right? Predictor class is going to be multi-class. So it's going to be predictor type. And then number of classes, which should be down below. We're going to actually set to 10. Hello, number of classes. You should be at the bottom. The rest of this we're not going to mess with. Notice that this is a rabbit hole, right? For the exam, no. For your model, maybe, right? This is a rabbit hole to go down. You know, and this exists outside of SageMaker, right? If you've ever done any kind of hyperparameter optimizations, then you've had to deal with this before, right? What is our targeted recall? What is targeted precision? What is the number of like all that stuff? So if you're going to do optimizations, yes, you're going to have to come in here and really deep dive into this to really peel it back. You know, there's a whole actual day immersion just on hyperparameter optimizations from Amazon. So, all right, let's click on next. We're just going to leave that as is. As far as the input data, wait, was there something required? Oh. Did I put something wrong there? 200 to 500? No, that's right. Oh, you know what? There was one other thing I was going to change, which was the learning rate. Yeah. So. Yeah, I know. Okay, so we configured some hyperparameters. Links are there. And then here's our different channels. So these are our input channels, right? So we're just gonna actually put mode, I believe was file, no compression type, content type, data source. Oh, what was the path to the bucket data? Hold on. I think that's hidden somewhere inside of these slides. Hold on. For model training. Bear with me just 1 second. Because they keep changing the location. Let me give me just 1 moment. Let's see. Hold on. All right, we're definitely on training data. So let me grab that. And I don't think we're gonna add a particular channel here, so we're not gonna add like a validation or a test channel, although you could, right? Let's see, make sure I didn't miss anything. Oh, that's right. Forgot. Text CSV, multi-class classifier, feature dimension 6, and configuration. Actually, we will do pipe here because why not? CSV file S3, no prefixes, fully replicated. Oh yeah, and we're not going to share by S3 key. And then we're not going to do a checkpoint configuration. We're not going to do an out data configuration. So that should be good enough. Okay. Oh, did we have an output path when we did our training job? Hold on, because that's what they want me to model off of. Oh, yeah, gotcha. Let's open up a path. What do I have bucket wise that I can write to? By the way, you might see some weird names in here like test goats and stuff because these have to be globally unique. So I believe that I have an ML pipeline bucket that I can use. Yep. Let's make sure there's no special limitations here. No object lock. No, nothing. Should be good to go. All right, I'm just checking a few things and we're good to go. All right. Okay. No encryption key. Let's go for it. All right. Last thing is that, okay, so we created a job definition. We configured algorithm parameters. We define the data input and the data output. Now, the last thing we're doing here in this step 2 is, okay, what resources are we going to use to run the actual hyperparameter? Now, obviously, this is distributed or we were doing random. We could actually like add like tons of specific instances. But you know what? We're going to leave it alone. So we're not going to change anything. Let me just make sure. Configure resources. We're going to keep everything as default. Although, God, that really bothers me. Using an M4 XLarge. I just want to use an M5 XLarge. Let's just change that. We're not going to enable Spot, which enable it to use Spot instances. We're not going to mess with that. The maximum duration per training job. So notice this is defined in days, right? So we're basically saying, look, you can't run for more than a day, right? So I don't think there's anything else to set. Actually, hold on. We'll look at one other thing here. Algorithm is set. Input mode, we'll just specify pipe. Loss, range, batch size has been set to classifier. We set the learning rate values. We didn't change that. We set the number of classes. Okay, good. And then output configuration is that standard bucket. There's the source location for the training data. There's the training channel. That's the only channel we set up. Just verifying. That's it. Okay. And then we click next and then next. And so what that does is that now we, in a sense, have created the training job definition, right? So it's funny because we were in hyperparameter, but we created the training job definition, which is why they had me use the same setup for training job. And then here, for example, I'm going to set concurrency for that particular job, set it to 3, right? And the maximum number of training jobs that the job can run total, right, is going to be 10. So it's going to run them 3 at a time, and it's going to run a maximum of 10. So it's going to run through different iterations of that Bayesian search. Now, just a question for you. We choose, like in the demo, we chose the defaults, and I have 3 parallel training jobs, but what did I choose actually for my like optimization type? What did I choose? Does anyone remember? I chose Bayesian, right? Is that going to work if I'm going to run it in a parallel training setup? No, right? So just to say this is that I'm going to go back and take a look at this because I'm like, I don't know that that's actually going to work. So let's switch it to random. So again, this is where the like official demo notes probably need a little bit of an update because that's not going to function. All right, so there we go. We got the whole thing, right? Tuning strategies, random, linear learner, 3 concurrent jobs at the same time, 10 total training jobs. Let's do it. Then that creates the actual job. Now, at this point, it's going, right? So it's going to invoke the training parameters inside the training job. It's going to kick up 3 instances of the M5 size that I talked about. And then it's going to run that up to 10 times. So 3, 3, 3, and then 1, right? That's it. Now, the only part that was probably maybe like a little confusing is just all of the hyperparameter options that were there. That can be quite an eye chart, right? And so here it is for like linear learner, for example, right? The number of classes for the response variable. What else did we change here? I don't think we changed weights. I don't think we changed early stopping at all. Feature diminishment, the number of features in the input data, right? So this is just going to something that you'd have to just go in and learn, right? We talked about learning rate, but we didn't actually talk about that from a values perspective. So again, this is just something depending on the algo that you're using, where you're going to want to come in and see like how to optimize for this. This is a whole kind of like topic in and of itself about how you would like tune this, especially if you're not using automated tuning. But again, this is very manually intensive. It is highly recommended that you use hyperparameters to actually like figure out what the optimal parameter set is for your job in question. Okay. Questions? Okay. Other than like learning rate, I don't think they ask you anything that we haven't already covered in the slides. So don't feel like you got to memorize these. They're not going to ask you anything that hasn't already been like brought up in slides. Now, is it going to hurt you? No, but yeah, they're not going to deep dive into this. Okay. All right. It's 4:31. So I'm going to stop that recording. Oh, you know, a good question there is that was I actually done? Let's see. Oh, you know what? I think I just opened the wrong one. Let's close that one. And maybe I just opened the wrong ones altogether. I'm sorry. I'm kind of a hot mess over here right now. We're on feature engineering. Let's open that one back up. Okay. So this is where we just did the hyperparameterization job. Just know that when we do it tomorrow, I'll actually do a quick summary of like all the feature engineering transformation, you know, the mean variance standardization, min max, max abs. So I'll run through this like briefly again, just because we're about to roll into a lab and we just covered the material. So when we do it tomorrow, I'll just do a quick skim. Know that when you come in tomorrow, I'm going to have you start your labs pretty much around 9 o'clock, because I'm going to have you import your notebooks and run them. I'm going to re-review the material while everything's getting warmed up and ready to go. And then by the time you get back to your labs, it should have finished hopefully all of the rerun up to lab 3. And then you can just literally kick into lab 4. Now, I'm going to forewarn you, lab 4 does require a lot more patience because like, and I thought this was just outrageous. Like one of the jobs like must have taken 2 hours to run. So again, we're gonna do it before lunch so that we can come into lunch a little bit. But just be forewarned that tomorrow is gonna require a lot of patience. So if you have other side material or you wanna run practice exams, just know that when you're waiting for a job, you might just wanna switch over to another task. Because some of them are gonna be sizable. I've already raised the flag with AWS on that, so yeah, just be mindful.